This program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest UCTV programs.
Well, that was quite an introduction. I wish I had all the power that implies. But I have to say it was a pleasure. It's a pleasure to be here, and I thank the organizers, Mike and others, for inviting me to such a well-organized conference and with, in a sense, the right people. So although J. Caesar, the energy hub that Mike was referring to, is only about 3 months old, depending on how you count, and we're now we're out of the startup phase and into the research phase. Not a lot of people know our story. So I'm thrilled to have the opportunity to present our vision, our mission, some of the things that we're going to change in the battery R&D world. And I would welcome your feedback at the end when we have that opportunity. So you can see up here, let's see, our logo, which stands for electricity. Don't ask me exactly what, but I think you can get that feeling from that visual. Here are the messages that I'd like to deliver. The whole talk is right here. The opportunity for energy storage in transportation and in the electricity grid. It's unusual to find two such large energy sectors, in a sense, waiting for a transformation. The outcomes that we expect to achieve with our energy hub, they go by our signature sort of tagline, 555. It means 5 times the energy density, 1/5 the cost within 5 years. And I want to tell a little bit about why we have chosen to be so aggressive. Those are very aggressive. But beyond that, 3 legacies, I'll tell you what they are. And we hope that these will be transformational for the battery R&D community, as well as for the batteries that we produce. When you're going after such a big goal, you cannot rely on conventional technology. So lithium-ion batteries are the best batteries we've ever seen. They're everywhere in our pockets and in our cars, and they're growing by leaps and bounds. They get better at about 5% per year in energy density, and if you're looking for a factor of 5, you won't find it in lithium-ion. So we're looking exclusively beyond lithium-ion, so a new battery space. And we bring some distinguishing features, and I want to say a little more, actually, elaborate on something that Mike was saying earlier, about how J. Caesar is a microcosm of the DoE basic science and applied energy effort. And I'll show you that. I think it's really quite a testament to Steve Chu, who gave us such a wonderful talk yesterday. And in fact, this is his brainchild, and he gets a lot of credit for it. I think it's a brilliant and a bold idea. Okay, so let's launch. So here's the energy that we used in 2009. And the 2 biggest features there, if you see, are the yellow transportation, 29%, the grid, which is divided into 3, about 40%. This is about 70% of our energy. Both of those sectors are waiting for they're ripe for a transformation. In transportation, it's replacing foreign oil with domestic electricity. So a lot of good things will come from that, and reducing greenhouse gas emissions in the process. And diversifying, in a sense, the transportation energy chain. Instead of relying on one thing, oil, could rely on electricity, which comes from lots of places. But it needs energy storage for that to happen. The second opportunity in electricity, 40%. So the transition from coal to gas, we've already heard something about, being driven by lots of shale gas around, low prices, concern for the environment. That's half the battle. The rest of the battle is to go all the way to wind and solar. Lots of states say that we should have 20% wind and solar by 2020 or some other such RPS. And there's plenty of wind and solar out there. We could easily supply 30%, 40%, 50%, and lots of people say even more than that, up to 80%, from the resource that we are blessed with in the United States. So these are the two opportunities, and the bottleneck for both these transformations is energy storage. So J. Caesar was formed to go after this opportunity in a very special way. We have transformational goals, so 555, 5 times greater energy density than today's commercial batteries, 1/5 the cost, do it in 5 years. These are very aggressive. And everyone that I present these goals to says that, oh, they're so aggressive. There's 2 answers to that. The first is that's the opportunity, that's what you need to be transformational. So you could say, let's do something that's lower risk, let's shoot lower, maybe take a factor of 2 or a factor of 3, yes. It wouldn't have the transformational impact that a factor of 5 would have. So in both transportation and the grid, you have to compete. You have to compete in transportation with gasoline-powered cars. They have about a factor of 5 better range, many of the inexpensive ones. And in the case of the grid, you have to compete with backing up solar and wind with gas turbines. So you need to get the energy density up, that's for transportation, and the cost down, that's for the grid. So that's the first answer. We've put the challenge on the table and we're going after it. The second answer is take an envelope, turn it over, and a pencil, and ask on that envelope, what would happen if I did the best I could do theoretically, if I got all the breaks and I achieved the theoretical expectation for energy storage? And you might be surprised at the answer. It's a factor of 10. So in that context, a factor of 5, about half the theoretical expectation, that's what many mature energy technologies get. So in that sense, it's within reach. It's just a question of finding the new phenomena, storage phenomena, and materials beyond lithium-ion that will get us there. So there we quantify exactly what we mean in numbers. You can read that. There are also 3 legacies that we'd like to achieve. One is a library of fundamental knowledge about beyond lithium-ion energy storage. So we want to understand at the atomic and molecular level the phenomena and the materials of energy storage. And this is something that is not normal in the battery community. You're usually more concerned with, does it work? If it works better than what we have, we'll replace it. If it doesn't work as well, we'll throw it out, and we won't try to understand why. So this is a new feature, a library of fundamental knowledge. The second legacy are 2 pre-commercial prototypes, one for the grid, one for the car, that will achieve our 555 goals when scaled to manufacturing, very important. And the third one is equally important, a new paradigm of battery development where you put discovery science, battery design, and pre-commercial prototyping all in the same organization, highly interactive, talking back and forth across that spectrum, and accelerating the progress to the next generation battery. So here's the battery community at the moment. There are 2 parts to it, the science community and the technological, the engineering community. Each one is pretty effective, but they don't talk to each other enough. And that discussion in the vertical direction between the 2 communities is what we want to attack as our third legacy. Here is what J. Caesar will do, our visual. So on the left, you see the basic science, discovery science. We have 3 ideas, which I'll tell you about in a couple of slides: multivalent intercalation, chemical transformation, and non-aqueous redox flow, all of which are capable of contributing to this factor of 5 improvement. But more than, we have a cross-cutting science team which supports the fundamental research on those concepts. We have systems analysis and translation. We'll be building a battery on a computer. And we'll be modeling for cost and performance. And if we have, let's say, 16 ideas that emerge from the left, from the basic research, we'll model them all. Maybe 4 will be ideas that we want to send forward. They'll be the best 4. The other 16 won't work for some reason, won't work as well. And this modeling process will tell us why. It'll tell us where the weak link is, and we'll send that information, that challenge, back to the basic science side and say, make it better. And then we'll do cell design and prototyping. We have another innovative idea there, overseeing the prototyping with a translational development team, as we call it, which is made up of representatives from all 4 elements you see on this graph. That is basic science, battery design, of course, prototyping, and commercial deployment, so that any issues that arise or opportunities that might be missed can be identified and sent in the right direction, either back to the basic science folks for further work or preparing for commercial deployment. So there's a dotted line on the right between cell design and prototyping and commercial deployment. The center won't do any manufacturing. It's not our job. We don't have the resources for it. But we have commercial deployment folks and manufacturers on our team to keep us informed. So here's the team. It's rather large and I think very impressive. 5 national labs: Argonne, Lawrence Berkeley, Sandia, Pacific Northwest, and SLAC. 5 universities: University of Illinois at Chicago, University of Chicago, Northwestern, University of Illinois at Urbana, and University of Michigan for their automotive connections. And 4 private sector partners chosen strategically for the value they bring: Dow for its materials knowledge, and especially high throughput materials, which we would like to adapt in the center. JCI, Johnson Controls, the largest battery manufacturer in the world, mostly lead acid. They've got a catcher's mitt ready. They want to take what we develop and perhaps get ahead of the next generation of battery manufacturing. Applied Materials actually makes most of the semiconductor processing equipment for the industry, and that manufacturing challenge is much the same as batteries. It's lots of thin films, films on films, interfaces. You have to have film architectures. We'd like to benefit from their experience, and they're thinking maybe we can apply our semiconductor knowledge to a new field if it looks good. And finally, Clean Energy Trust. It's a nonprofit in Chicago, about 4 years old, that promotes entrepreneurship. And we believe there will be many opportunities for entrepreneurship, startup companies, and innovators in J.C.Z.R., and we've asked them to coordinate venture capital, bring venture capitalists and innovators together, and generally manage that part of our program. This is all bragging, so I'm not going to read it, but everything that our partners have done in the last 10 years having to do with batteries, you can see some of the things there and take a look at it later. But the team knows what it's doing in this space. We have more so that we have 14 partners, including Argonne. We also have affiliates. So I think the number is up to 45 now. These are organizations that don't get any money from J.C.Z.R., nothing from our contract with DOE, but they care very much what we do. So things like private companies, venture capital firms, trade organizations, research universities, and very importantly, energy frontier research centers. There are 5 of them that are battery related, and we've already had one big meeting with them to plan how we're going to cooperate in attacking this space. So these folks are interested in what we're doing. And we imagine, for example, having a big workshop every year. We invite our affiliates. We have our J.C.Z.R. folks explain what they've done in the last year, what they're planning to do in the next year, and we fully expect some of our affiliates to hop up and say, see, you're working on XYZ, I'd like to work on that with you. I know something about it. I can make you go faster. Or, I'd like to work with you on that. When you're done with it, give it to me. Let's start talking now so that we can see what the transitional issues will be. So we want to bring the whole community up with our effort. So I mentioned before that there are 3 concepts, and here they are: multivalent intercalation, chemical transformation, and non-aqueous redox flow. Let me tell you very briefly, and I'm sure this audience will understand instantly exactly what they are and why they're valuable. So on the upper left, you see a typical lithium-ion battery. A lithium-ion oscillates between the anode and cathode, stores energy, releases energy, has 1 charge. So why don't you replace that lithium with an ion that has 2 charges, like magnesium, or 3 charges, like yttrium or aluminum, and double or triple the energy density in one fell swoop? So that's the first idea. Second idea, chemical transformation. So instead of having intercalation at the anode and cathode. So in graphite, for example, the layers spread out a little bit, the lithium ion goes in, the lithium ion comes out, and the layers shrink. You store some energy that way, but you can store a lot more energy with a true covalent chemical reaction, a covalent bond. So why don't you replace the intercalate host with something that actually reacts with it? Examples are lithium with oxygen, lithium sulfur, sodium sulfur. These things have been around. There are lots of other opportunities besides those. So you can get a factor of 10, for example, in energy density on the back of an envelope with this approach. The third idea is non-aqueous redox flow. So why don't you take that solid electrode and replace it with a liquid? So when you have a solid electrode and a working ion, you have to have structural compatibility between these two. It restricts the space of working ions and cathodes that you can survey. So almost anything can be put in solution. So if you're dealing with a solution or a suspension, it greatly expands the range of materials that you can look at. And especially I've put down here in the bottom an organic, symbol of an organic material. There are lots of organics that are virtually unexplored that you can use for both the electrolytes and for the redox couples. So that space is huge, and it doesn't cost much. So you can reduce the cost by going for the cheap working ions and redox couples, and you can store as much energy as you like because you pump this liquid electrolyte, the catholyte, out into a big tank out in the field, and you don't care how big it is. So these are the advantages of these three ideas. We're going to apply lots of tools, so characterization tools. We need to put everything into one brain or a few brains in order for this to work, and that's a central idea with J. Caesar. We want to understand at the atomic and molecular level so we can build the battery from the bottom up. And we want to integrate the latest techniques in situ, time-resolved, multimodal characterization and make them work together. Here's one of the distinguishing features we bring, an electrochemical discovery lab. So this sort of shows a loop, a closed loop that shows how we'll intellectually proceed. I'll tell you in a minute about some genomes that we've designed to look at anode and cathode materials, and also a very innovative electrolyte genome, look at the liquids. We'll take the results of those genomic surveys, choose the best materials, and synthesize them in this electrochemical discovery lab, and move the synthesized thin film or single crystal, whatever it is, along a chain and measure 6 or 7 different characterization steps, which we can rotate in and out, whatever we need, without ever losing the protective environment. So this gives you a way of comparing properties on the sample measured systematically and consistently, and materials measured by the same techniques, one against the other. So you can get the trends in what's going on. We'll also be able to do composites. Batteries are built on composites. So you want to put two materials together, look at the interface, look how they work in concert. And the things that we like will move on to the cell design and prototyping and the techno-economic modeling stages. So we'll get certainly challenges out of this, which will go back to the basic science side, and we'll end up, we hope, with our prototypes from a technique like this. So I mentioned genomes. Materials genomes have been around for 5 years or more, and they've already been applied to cathodes and anodes. We have a program, a very extensive program, that will continue that, extend that effort, but we're introducing something new, an electrolyte genome. So the electrolytes are a huge class of materials, probably bigger than what you would consider for anodes and cathodes, and you can tailor them. So here on the upper right, you see quinoxylene basic unit. You can hang ligands off it. Depending on what ligands you hang off it, you can make it either insoluble or highly soluble. You can make it very electroactive or not at all electroactive. And in general, you can do this with lots of backbones and with lots of ligands. And you need a way to, a guide to help you figure out what that space looks like. And that will be our electrolyte genome. So usually genomes are not applied to liquids. The problems are totally different. You have, for example, a solvation shell that you see in the lower right. When you have doubly charged ions, the solvation shell is very different than when it's singly charged. And that solvation shell, as it moves into an anode or a cathode, has to get lost, and the central ion has to be transferred across an SEI into, if it's an intercalation material, into the intercalation host. So those are the kinds of things that we're going to look at with our electrolyte genome. So here's our mnemonic again, our visual. Let's talk about the systems analysis and translation. We'll design on the computer, again, from the bottom up, knowing the materials and their performance and their cost, how a battery system composed of, let's say, 3 of the materials would work. And we'll look for 2 metrics. One metric is performance. Will it help us meet the 555? And the second one is, so that's the first 5. And the second one is manufacturing cost. So will it help us meet the second 5? So we'll know before we actually make these batteries what to expect. And as I said earlier, we have 20 designs. We'll move 4 of them forward. The other 16, we'll ask, why didn't they work? And we'll find the weak link in that system, and we'll send that problem back to the basic science side and say, here's the issue with this battery, make it work. And this is a thing that you can't do unless you have a single organization that talks to itself across this R&D spectrum. So that's the battery on a computer. It's a little bit like materials on a computer, so the genomes will do the same thing for us at the materials level. The techno-economic modeling does it at the battery systems level. And we'll move the successful ones onto cell design and prototyping. And we have a new idea there. So I was mentioning these transitional development teams. You see a circle, a ring, with 4 colors. Each one of those 4 colors represents a step in the J. Caesar diagram. So the basic science side, the techno-economic modeling side, of course the prototypers and the commercial development, and this team will look at everything in the prototype. We'll want to make the prototypes, but we'll also want to break the prototypes. So why do they fail? Why don't they work better? And this team will go after those failures as well as successes, and once again, send the failures back to the basic science side and say, here's why it failed. Help us make this better. And again, that's a feature that you don't get unless you have a highly interactive organization. So another feature, we're going to kick off our translational development teams on day 1. They've already started with the idea of going after a magnesium intercalation battery and a kind of non-aqueous redox flow battery, again, to get the system working and develop those challenges, not that we expect these prototypes to be our final ones. Here's some pictures of the prototyping teams and the parts of J. Caesar that they represent, all smiling and ready to go, and in fact, already working. We have a very interesting intellectual property plan, which was completely signed before our proposal was submitted last May. It has at least two interesting features. First feature, no exclusive licenses. So we're not going to be giving anybody a break. If one of our commercial partners works with us to develop some of the IP, of course they may get special treatment, a slightly more favorable deal at the end of the process, but they won't get an exclusive license, and everyone has agreed to that. The other interesting feature is that by agreement, Argonne will be the negotiating agent, so an outside entity that wants to come in and pick up some IP doesn't have to talk to all 14 partners. They can talk to just one agent who will, of course, consult with the other partners. So we hope that this will accelerate the transition to manufacturing. So I want to emphasize now that the three concepts I talked about, multivalent intercalation, chemical transformation, and non-aqueous redox flow, are not battery technologies. These are concepts. We want to find out everything we can about the way they operate, the phenomena and the materials, and we expect that the batteries we make will draw from all three of these threads. So they will integrate features from every one of those three concepts. So here is a battery that we might make. So on the left-hand side, you see it might be a multivalent metal like magnesium, which serves as the anode. We'll take an electrolyte from our electrolyte genome and our electrochemical discovery lab to transfer that ion to the other side. We may have a flowable electrode, so the cathode might be a liquid, not a solid. And immediately you see, I mean, it may have chemical reactions, of course, taking place in that solution or suspension. So immediately you see that we draw from all three concepts. So we expect our batteries to be really quite innovative. And finally, I want to share with you this idea that J. Caesar is a microcosm of DOE's spectrum from discovery to deployment. And here you see our J. Caesar, again, visual, with the basic science on the left, the discovery science, the battery design in the middle, the prototyping, and the transfer to deployment on the right. And on this lower strip, I'm showing you words that DOE uses to describe itself. So on the left-hand side, grand challenges. I'd like to understand why this works. I don't know what the application may be, but it's an important challenge that we are now able to do. We will access anything that comes out of the grand challenge effort in DOE, the science effort. We have our own discovery science teams. How do batteries work? What are the phenomena? What are the materials? We have use-inspired basic research. So that means I'd like to make the cathode better. How do I achieve that? What do I have to do to make the cathode better? Right? And of course, there's basic science there. So everything you see on the left is phenomena-based, discovery-based. How does it work? Everything you see on the right is performance-based. I want it to work better. So the applied research, give me another 10% in performance or another 50%. And for commercial deployment, technology maturation, and manufacturing, we'll work with our partners starting now to help them to make that happen. So this is quite a new idea, and Steve Chu and his colleagues, and of course based on Bell Labs and the bioenergy research centers, which preceded us by about 5 years, these two models, and we're very hopeful that it'll work. It's the interaction that counts. I've shared this with others. I think our biggest challenge actually is not brains. I think we have a lot of smart people and smart organizations on the team. Our biggest challenge is communication. We have to make this communication happen two ways across this R&D spectrum. But if we can do that, then I have every confidence that we'll be able to accelerate the process. That's a key goal, number one, and number two, achieve our 555 goals. So thank you.
Thank you, George.